And today we have a distinguished speaker, Sasha Phillipov, and his background is pretty strong. He came from Russia, from the Physical Technical Institute to Princeton, where he was on the graduate program, and he was an Einstein Fellow. Spent the year, I guess, a year in Berkeley. Then he moved to CCA for 4 years, and finally, maybe not finally, who knows? He is a professor in Maryland, College Park. He is recently he received Sloan Fellowship, so we can congratulate. That's really news from just 2 days ago. It's also a part of the collaboration and a big grant provided by Simons Foundation, and he is a superb, and I would say one of a kind expert in both theory and simulations of pulsars and black holes, mostly high energy stuff that we have from them. We see various processes like cascade, like emission that goes on, reconnection and everything. So if you want to know anything about pulsars or black hole magnetospheres, he is the person to talk to. He can tell you theory, he can tell you observations, he can tell you simulations. He is a great expert. So, floor is yours, Sasha.
Okay, so now I just have to leave because I cannot say anything better to match with what Misha advertised. Okay, thanks so much. Many of you heard my recent talks about black holes, so I decided I'll talk about neutron stars instead, so that some of you hear something new. So in this talk, I'm gonna go through how this surroundings of rotating neutron stars work and how they power electromagnetic emission. They're pretty remarkable objects. They power electromagnetic emission across 20 orders of photon energy, going from radio waves to what's now known as 20 tera electron volt pulsed emission from the Vela pulsar. And behind all of this spectacular electromagnetic radiation, there is some plasma physics that accelerates particles and makes them shiny. So I'll go through some of the details in the talk. So to remind you what these objects are, these are rotating neutron stars. They are remnants of collapses of massive stars. They have masses from 1 point something solar mass to 2 point something solar mass. They're spinning with periods from a few milliseconds to a few seconds. So they're very quick rotators, and they also are equipped with huge magnetic fields. So we know that some of them have magnetic fields as high as 10 to the 14 GeV. So those are probably the highest magnetized objects in the universe. The whole activity of these objects is powered by rotation. So you have this small, very dense ball of matter, this neutron star, and it has a magnetic field. You start spinning it. What you start having is what's called unipolar induction. So rotating magnet generates electric fields. So in the frame of the star, the electric field is 0. That means in the laboratory frame, there is electric field. And part of this electric field will go outside into the magnetosphere. If you solve equations in vacuum, you'll find that part of the electric field directs along the magnetic field outside of the neutron star surface. So what it starts doing, it starts pulling out charges from the upper layers, from the atmosphere. It can be electrons or protons. And then these charges quickly accelerate because this electric field just pulls them and they quickly reach high energies because the field is so strong. The magnetic field is of order 10 to 12 Gauss again. So as long as these charges reach energies corresponding to Lorentz factors about 10 to the 7 for electrons, they start to emit GeV photons. These photons come about because the charges flow along curved magnetic field lines, to first approximation dipolar. And as they're doing so, they're experiencing acceleration towards the local center of curvature. That's what we call curvature radiation. Because they don't go on straight field lines, but on curved field lines, they create these GeV curvature photons. And after they travel finite distance, of order of tens of meters in this environments, they get converted into electron-positron pairs. This happens because there is a 10 to the 12 Gauss magnetic field. There is a finite probability for a photon going across the field to decay into an electron-positron pair. So now you have two charges, electron and positron, instead of one charge. And they also get kicked by this electric field. They accelerate and they create new photons. Photons decay again. There are new pairs, and that's what we call pair avalanche. Starting from one single electron extracted from the neutron star surface, you get many of them. So that's the one of the phenomena that I'll come back a lot in this talk. So that's how this environment gets filled with electron-positron plasma. They're not just rotating magnets in vacuum, but the surroundings of them, the magnetospheres, are filled with electron-positron pairs. This pairs, the plasma, they modify the magnetic field because they drive currents. Currents change magnetic fields. Charges change electric fields via the Gauss law. And the initially dipolar magnetic field gets modified. So that's another problem to figure out how the magnetic field is looking like. And the ultimate goal is to explain the observed emission. So you see the whole zoology for the sources. Sometimes, as in case of the famous Crab pulsar in the center of the Crab Nebula, you see that the emission from the radio, this is the radio, all the way to the gamma rays come at the same rotational phase. So this is a dependence of intensity versus rotational phase. The pulsar is rotating and you see its emission once or twice per period because of the lighthouse effect. And the peaks in radio may be the same as in gamma rays, or it can be different. In Vela, for example, you see the radio peak, but the gamma rays are at different phases. So that just means that there are multiple regions around the neutron star where the particles get accelerated and the non-thermal photons are produced. There is not just single physics mechanism, but probably plenty of them. This is the one appearing in Paris. So to give slight illustration, they installed the pulsar on the top of an Eiffel Tower, as observed in November of the last year. This one is spinning very slowly. If you heard, there are these new objects called slow rotating transients or something with periods for like weeks or something. We don't know what these are, but this one spins at exactly 1 minute period. So that's actually quite a good candidate, I would say. So you don't see the beam because of the zoom, I think, but basically what happens is that this thing emits light and the sphere rotates, and that's basically what the radio beam for pulsars is doing. You have a small region close to the neutron star that radiates, and as the neutron star rotates, that beam either points towards you or goes out of the line of sight. That's why we see two concentrated peaks and periods. So the question of why pulsars pulse is very simple, just because they rotate quickly. Why they shine is more complicated. So the cartoon for everything that happens in this magnetospheres has been derived by Peter Goldrack and Julian in end of 60s. Basically, what they considered, they didn't think about the pair creation, but they already thought about the particles extracted from the atmosphere. They said, okay, the selections, they go along the magnetic field, and that's why they need to drive the current. So the electrons extracted from the atmosphere, they create the current. The current is along the magnetic field, and then you basically have a current wire with a single field line that creates a magnetic field toroidal with respect to the direction of the current. So that's the magnetic field out of this plane. This is d phi. The magnetic field of the dipole is in the plane. The d phi is out of plane. So that's one is created by the current. And the second fact is that the plasma, it wants to correlate with a central object because it wants to screen the electric field. I'll talk slightly in more details about this later. And basically what you have is that the whole plasma outside of the magnetosphere, it wants to move together with the rotating neutron star. As it's doing so, it's creating electric field. So the velocity of the rotation of the plasma vector product with the magnetic field gives the electric field. So that's E theta. It's responsible to the rotation of the neutron star. And then you have a vector product of the electric field of rotation cross with this B phi, the toroidal field created by the current. The Poynting vector is outside, and that means there is a electromagnetically dominated wind from the source that leaves out to the surroundings. So that's how the pulsars are losing energy. They convert rotational energy of the central object into a Poynting flux dominated wind. By what I mean here is that the energy density in the magnetic field that leaves the neutron star is much bigger than the rest mass energy density of the plasma. That's what we call a sigma parameter or magnetization. It basically measures by how much the magnetic field is dominant the dynamics of the plasma compared to the rest mass effects. So the pulsars lose energy, Poynting flux goes out. That means that the central object loses energy, and we can actually measure it. We can measure how quickly the period of the central source increases with time. And converting that into the amount of energy, we can actually figure out magnetic fields by equating the power lost into this Poynting flux to the loss of rotational energy. And that's basically consistent with the 10 to the 12 Gauss field for an average neutron star. Okay, so how do we actually do something with this cartoons quantitatively? So the first sort of approach to use is what's called the force-free paradigm. It's a very simple approach. It basically says that you can assume just two things about the plasma. One of them is this one. This is the momentum equation for the plasma. The gray is not very visible, but you can believe me that what's written here is a time derivative of the momentum of the plasma, and here there is a word pressure, so there are terms like time derivative of the momentum of the plasma and gradients of the pressure, so that's the usual terms in the momentum equation. And on the left there is a Lorentz force. So the plasma is charged in relativity. So there is a net charge density. This is the electric force acting on the plasma. This is the Lorentz force. And on the right-hand side, you have terms that scale with either pressure or the density of the plasma. If magnetic fields are very strong, by the assumption from the previous slide, you can basically neglect all of this. B squared is much larger than everything else. You can drop this. And what you get is a very simple picture. You get the Lorentz force equals to 0. Okay, so that's why it's called force-free, because the net Lorentz force acting on the plasma is just 0. The second important assumption is that the plasma doesn't tolerate electric fields along the magnetic field. And that's quite simple to visualize. If you put electric field on top of the magnetic field and then you put plasma particles into it, electrons would go one way, the positrons would go the opposite way. They would create electric field that would screen the initial electric field that I've put in the system. So what it's doing is basically screening out all the electric fields along the magnetic fields as long as there is sufficient plasma. So the two assumptions to this picture is basically that the magnetic field dominate, and the second assumption is that there is plenty of plasma so that electric fields get shorted out. It turns out if you take these two pairs and Maxwell's equations, you can actually formulate the expression of the current as a function of just electric fields, magnetic fields, and its derivatives.
Plenty of plasma means both high densities and well ionized or one of
Yeah, so here in this environment, everything is 100% ionized. The densities are quite low, but you don't need much to screen the electric field. I'll describe this in a bit more details later. That's what I call plasma without the plasma. I said there is plasma, but the equations don't know anything about the plasma. Everything they know about is electric fields and magnetic fields. So electric fields and magnetic fields are dictating the plasma what to do, and that self-consistent feedback describes the evolution of the electromagnetic field. You can formulate this as a set of hyperbolic equations, d dt equal to something that depends on the electric field and magnetic field, and same for dB dt, and plug it into the computer and solve it. So that's what's been done in end of 2000s, and this is an example for a magnetosphere where the magnetic moment is aligned with the rotational axis. This is what's called an axisymmetric pulsar. The black lines are the magnetic field lines. You saw them initially dipolar, and as the simulation started, they opened up. and created something that looks like a Goldreich-Julian solution. So some field lines remain closed, some start on the star and live to infinity near the starting on the pole. And then beyond certain surface, which we call a light cylinder, and I'll explain in a second what that means, the polarity of both field components, the one in the plane and out of the plane, change, and you create a surface where basically all the components of the magnetic field change sign. Okay, so the poloidal field changes sign just because the field lines are living out in the northern hemisphere and returning back in the southern hemisphere, and the toroidal field changes because there is a different direction of the current. So here you create a region where magnetic field goes through zero, and that's where, I'll discuss later, magnetic reconnection happens and converts the energy from the magnetic field into the plasma.
How are the boundary conditions set?
Right, so you assume that the neutron star is a perfect conductor, which is a good assumption. The lifetime of the magnetic field on a neutron star is more than 1 million years, so for one rotation, you can assume perfect conductor. And everything you need is for electromagnetic fields, you need to set up the normal component of the magnetic field and the tangential component of the electric field. The tangential component of the electric field comes from omega cross r cross b. So you know how fast it's spinning, you assume normal component of the field, let's say it's dipolar, and then you have everything to specify the problem. Far outside, we put something like what's called an absorbing layer, which damps the field to certain configurations. So in this particular ones, we force the field to be radial, but luckily the signal from beyond the light cylinder cannot communicate back, so as long as it's numerically stable, it doesn't matter. So the surface light cylinder is special. This is where if the plasma wants to correlate with a central object, it would have to do it with the speed of light. So here omega times r is 1 or c, and beyond that the field lines have to open up so that the plasma doesn't rotate together with the star, but just slides out to infinity along the open magnetic field lines. That's what it's doing here. And inside the reconnection region, some interesting dynamics will happen that I will describe later. What you have to understand about this model is that it breaks inside this current sheet. So here the B field goes through zero, and the assumptions of this equation are violated. This term is no longer dominant on top of the pressure and the density. So here you need to include more physics, and force free doesn't capture it anymore. And this is one of the regions where the particle acceleration and emission is happening. So to explain observations, you actually need to go to some other models. And the second thing it assumes is that the plasma supply is a guarantee. I said just the plasma exists, and that's not always the case. It's supported self-consistently by the pair creation region. So in order to model this consistently, you need to understand both how the pair creation happens and how reconnection occurs. So in order to do this, we use other numerical techniques. This is what's called particle and cell simulations of different kinds. This is the most fundamental way to model plasma, in particular collisionless plasma. So the plasma is of low density such that the Coulomb collision time is much longer than the all dynamical times in the system. That's the case near the neutron star and near low luminosity accreting black holes. So what you can then do is you can represent your plasma as an ensemble of big macroparticles that represent a collection of billions of real particles and simulate their dynamics together with the evolution of the magnetic field. So what's happening here is that you have a computational cube. At every grid point, you have electromagnetic fields that are defined. And then you have particles moving through this computational grid. They experience Lorentz force that acts on the plasma. If you know the electromagnetic fields, you can then push the particles according to this electromagnetic force. You can then what we call deposit currents on the simulation grid. So to calculate the currents that the moving particles are creating, then use them as a source in your Maxwell's equations, solve the Maxwell's equations again, find new electromagnetic fields, and continue the same loop over and over again. So the added benefit is that you're resolving plasma dynamics. You can create non-thermal distributions, so really anything that the plasma can do The downside is that you need to resolve the scale at which this dynamics is happening. So in particular, you need to resolve what's known as the skin depth, the speed of light divided by the plasma frequency. This is where most of the plasma physics phenomena is happening. This scale in realistic systems is very small. So I'm talking about centimeters for real neutron stars, or tens of centimeters at the light cylinder. So the size of the real object is 10 kilometers. So obviously, as with almost any computer simulation, you cannot simulate the real system. You have to simulate a downscale system, and then to understand how the changing in the separation of scales changes your conclusions. And with many of these phenomena, we have some understanding of what's going on as you change your effective Reynolds number. With some of them we don't, and that's an ongoing research. What you have to sort of add to simulate the environments of neutron stars and black holes is that sometimes your particles become so energetic that the photons that they're emitting exert a sufficient force on the accelerated particle and substantially change their momentum. So that's what's called radiation reaction force. The moving particle, the accelerated particle is emitting photons. The photons remove the momentum from the particle, and need to take this into account. So the code is adding this radiation reaction force to the Lorentz force and self-consistently calculates how much photons the particles are emitting, and then deposit them as a separate species on the grid, propagate them together with the charged particles, and for some prescriptions, create electrons and positrons in the simulation box. To model black holes, we also include general relativity, and it is important for recreation flows of the neutron star itself, but I'll not go into details about how this is happening. You can talk to me later about this. So I'm done with the introduction, and next few slides, I'll show how these magnetospheres are looking like in different approximations, and how they produce the various high energy emission that we see from this object. The first example is what's called the Goldreich-Julian pulsar, the pulsar that doesn't sustain percreation and just has this atmosphere on top of a neutron star. So here the boundary conditions that on top of this rotating conductor that was there in the force-free simulation, here I'm also adding a thin atmosphere of real charges, positive and negative charges, that are provided for the electric fields that are created by the rotation to be pulled out into the magnetosphere and fill it with plasma. So what you get instead of this solution with open field lines, currents, and all this nice activity is something very different. So here you get a finite cloud of electrons near the magnetic pole, and a disk of protons or positive charges in the equatorial plane. That happens because as you start the simulation, the initial electrons that are launched by the electric fields outside, they quickly reach high energies and basically leave the system, leaving the central star charged.
This density?
Yeah, this is density. So what you basically get is that the total charge of the system is non-zero. And as the electrons are pulled out from the upper layers of the atmosphere, they're initially pulled back by this rotationally reduced electric field. But as they go out, they start to feel the charge of the central star and just fall back. So they're bouncing back and forth in this dome. And the only way for this positive charges in the equator to leak out is this non-axis symmetric instability that you see. You see this wings of positive charges that are trying to leak from the system. So why is it happening? Is it because this disk is rotating differentially? It doesn't have enough charge to co-rotate precisely with the neutron star as it would do if there would be enough plasma. It rotates differentially. The angular velocity of the plasma changes as I go through the disk. And that's unstable. For a normal fluid, this would be called the Kelvin-Helmholtz instability. For the plasma that consists of one sign of charge, this is what's called a diachatron plasma. Diachatron instability. What it creates modulations of the charge density and the electric field in the phi direction. And then the perturbed E cross B drift makes the particles basically move away from this cloud. as you run the simulation, you can calculate how much current these clouds are actually creating, and numerically we find that the current is very small. So it's not substantial enough to create the fully open force-free magnetosphere that the force-free simulation predicts. So we think that this is the actual state of all neutron stars which span down sufficiently enough such that they're not producing electron positron pairs, and we think that's how they're looking like. There is plenty of them as they cross the what's called the death line in their population, and are just sitting there without doing much.
Do you prescribe some fixed charge for this cloud that you put at the beginning, or is it allowed to leak, or that time scale is very long?
Right. So here, basically on the surface, we create an atmosphere of sufficient density, and then its density exponentially declines because of the gravity. So the thermally leaking particles are basically, its amount is very small. It's not sufficient to drive anything. You only extract particles when you develop electric fields. And then you extract just enough, the electric field at the surface gets screened, and that's basically a steady state. You only need to provide new particles if there would be some leakage of the particles to infinity, and then you would supply new ones to reach a steady state.
Can you tell us which way is it rotating?
Good question. Clockwise.
So these are like leading spirals,
Yep.
which is weird.
Yeah. Actually, I can talk to you more about this. This is not so important for what I'm gonna say. So that's how they look like if you implement the sufficient amount of pair production. This is a pulsar that is inclined by 60 degrees. By that I mean that the magnetic axis is 60 degrees inclined with respect to rotational axis. And in laboratory frame, the whole thing is spinning. The magnetic axis is going around, and this movie is plotted in a frame that basically moves together with the magnetic moment. The magnetic moment of the star is sweeping through the box, and I'm sitting on that direction and plotting it in a frame that moves together. This is not the Lorentz boost, so I don't have to violate causality as I go beyond the light cylinder. This is just a coordinate transformation. I basically transform my azimuthal angle such that it moves together with the rotation. The white lines are the magnetic field lines. In that frame, you basically see a steady state. There are field lines starting up close to the magnetic pole and reaching to infinity. There are same closed field lines, similarly to what you saw in the axisymmetric force-free movie. And beyond certain surface, there is this wiggly cloud. This is the same current sheet that in the axisymmetric movie was basically just a disk, disk in the equatorial plane. Here it's tilted. That's what's known as a ballerina skirt type current sheet, similar to one that you see in the heliosphere of the sun. And inside this current sheet, you see a dynamic reconnection going on. So this field line, for example, was closed and then it opened up. Then it can close again as this field line did, and then opened up again. So there's a dynamic plasma process operating inside this current sheet basically all the time. In this movie, you see a slice through this three-dimensional movie. This is the plasma density. You see how the current sheet was created. It was first thick, it then goes thinner and thinner, and at some point it disrupted itself into instabilities. And from the studies of this current sheets in paraplasma, we know that there are two instabilities. One of them is called the tearing instability. This is a fragmentation of the current sheet into a sequence of what we call X-points. This is your familiar Sweet Parker cartoon from Wikipedia, from any plasma physics textbook. Basically, they postulated that two field lines are coming together, reconnecting, creating these outflows. And thinking of this as a steady state, this region is what's called an X point. Here, the magnetic field actually goes through zero, and these regions are outflows. They go with roughly the Elfin speed. And the advancement through simulations and initially through theory by Nuno Loureiro in 2007 is that if you do this in 2D for a large enough system, there is never a steady state. The whole system wants to continuously get fragmented into sequence of X points and growing blobs of the magnetic field, which are called plasmoids. And these plasmoids are merging, coalescing into bigger and bigger structures. They form self-similar distributions as across the scales. And basically, the particle energization happens inside this X point. So this is where they're coming in, feeling the electric field. Remember, the magnetic field is zero here. Nothing can deflect them efficiently away from this X point. They just go down the electric field initially and get certain energy. So that's the place where they first get energized. And turns out that's the most important region in this neutron star environments, because as they get leaking to this blobs or plasmoids, there is magnetic field inside these blobs, and there is synchrotron cooling. The cooling time for these particles inside current sheets is very microscopic. It basically happens on a time scale of one Larmor orbit. As soon as they get kicked out by the electric field inside the 6 points, they quickly lose their energy. So that would be the basic idea how the gamma rays are produced in these environments. The particles are entering the current sheet from the upstream, get their energy, and then quickly radiate their momenta through synchrotron radiation. The other interesting region is near the pole. You see separate clouds of electrons and positrons leaking from this polar region. And this is where I would argue the coherent radio emission of pulsars. If you remember this region, remember the intermittency that these clouds are continuously produced as separate entities. And I'll explain what's going on towards the end.
Is the emission in the current sheet in?
Yes.
Why?
Like
Like similar to cone to pulse?
Yes, that's less trivial. The beaming arises mostly because of the fact that the particles very quickly start to going along the magnetic field. And there is what's called a caustic effect on this magnetospheres. Basically, you see the emission across the extended region inside the current sheet to arrive towards you in the same phase. That's because the current sheet is rotating and expanding relativistically. And then basically the photon that was emitted closer to the star catches up with photons emitted further away into a single phase. So if you compute the light that is coming from the particles in the simulation, you start to see two peaks. You see a moment where this whole extended field line right now produces emission that points towards you. This is this colored region. This is the photons that are beamed towards you as an observer. And then the second peak you see from the outside of the neutron star, where the particles are coming back towards the neutron star and beaming the same photons towards you. So that's why Fermi sees two double peaks, and that's why the peaks are narrow. They're narrow because the light in a single peak is not some given hotspot, but the whole field line basically from 1 to 2 light cylinders beaming photons towards you into the same phase. You also see the small scale variability on top of the light curve. That happens because the current sheet is unstable. It's dynamic on small time scales. In actual observations, you cannot see this. This dynamics happens on microsecond scales. You cannot have gamma ray timing on the same time scale, so you'll never see this. We do see variability in radio, and I think in radio you have lots of probes into what happens in the current sheet, and hopefully I'll have time for this towards the end. So on top of that, you can explain this caustic emission in two peaks. You can also calculate the efficiency. This is just the amount of energy that this is dissipated inside the current sheet from 1 light cylinder to 2 light cylinders. As you go much further away, the wind gets very relativistic, and at that point, the dissipation drops. So 1 to 20% is how much magnetic energy is dissipated in reconnection. You just have two opposite field lines, you dissipate them inside this current sheet and convert it into plasma particles. The plasma particles, again, quickly lose their energy to synchrotron, and that's why the dissipation immediately gets converted into photon.
How did you make this plot? So this is from, you take a PIC simulation and you get some distribution of the particles, and then you do radiative transfer after that?
Luckily, you don't need to do basically any radiative transfer, because you basically have a single photon. a single particle, you can calculate the amount of power that this particle is emitting just because you have perpendicular velocity to the magnetic field. You then release them as photons, and then they go in straight lines, and I collect these photons on the sphere.
And then you're coloring based on photons that arrived at some.
Yep. Yep, basically on the same time that this light curve is computed.
But the peak simulation is not a global simulation. The whole thing is a little box somewhere.
Well, this is the whole simulation of the whole thing, literally. So here you have, the star and the current sheet and everything.
But you, at the beginning, you said it was impossible because you needed this.
It's impossible to simulate it with the same ratio of scales. What we do here is that basically our skin depth is not a centimeter, but much bigger. The catch here is that as long as your current sheet is bigger than 100 skin depths, its dynamics in terms of creating the so similar plasmoid shades is quite similar. And the rate of reconnection, meaning that how much energy gets converted from the magnetic field into the plasma, is basically converged. So it doesn't matter whether I would do a current sheet that would be 100 skin depths wide or 10 to the 5. The rate of converting magnetic energy we think would be the same. The properties of the turbulence and dynamic range, of course, would be different. But this key property about how much energy gets leaked from the magnetic field into the particles, we think would be similar. And the second argument is that for the dynamics of highly accelerated particles, it actually doesn't matter because their cooling length is also microscopic. So they basically get cooled on the same skin depth scale where the reconnection happens. That's a luxury of this environments, I guess. So you can compute the light curves. These are light curves computed for different inclinations. This is 30-degree inclined pulsar. This is 60-degree inclined pulsar. You can cut them at a certain viewing angle and get different dependencies. So you generally see these two peaks that are representative of Fermi light curves. And sometimes you do get an emission in between the peaks. This is a feature of the low inclined pulsars in these models, and you also do see them in observations. Okay, so you also want to know what happens with the spectrum, and for that we actually run local simulations to get larger dynamic range. This is the local simulation of reconnection with strong synchrotron cooling. This is work by my student Sasha Phillipov, who will start at the Institute as a fellow in September. So you get to know him a bit. The conditions in the systems are such that the field is around 10 to the 12 Gauss at the light cylinder. The magnetization on top of the current sheet is still large, it's highly magnetized. And you could see that this is basically a characteristic Lorentz factor that the particle gets if the magnetic energy gets transformed into the plasma. So if you convert b squared over 4 pi into the plasma energy that has the rest mass rho c squared, that will be a characteristic Lorentz factor that the particle would get. And that's indeed consistent with the simulations. We see that pairs get accelerated to this energy of few times the sigma, and then they quickly radiate their energy into synchrotron emission. There has been a paradox, which is known as the burn-off limit, is that if you assume that the acceleration and emission of the plasma particle happens in the same place, your synchrotron emission is limited by a fundamental constant, which is 160 MeV. For a connection where electric field is only 1/10 of the magnetic field, you get 16 MeV. And there have been multiple attempts to see whether you can create synchrotron photons in excess of this limit. I think this is the most consistent demonstration that it's only possible if the magnetization parameter exceeds what we call a burn-off limit. This burn-off limit is basically the critical Lorentz factor at which the electric field balances the losses. You cannot accelerate beyond that Lorentz factor. But you can do this inside the reconnection layer because you accelerate particles right where the B field gets close to zero. So in the small exponents, they get to energies to few times sigma. And as they get diverted away into this region with denser plasma and magnetic fields, they radiate their energy, you get synchrotron. And theoretically, we can explain that the peak frequency that they would be emitting would be above 16 MeV by this factor, sigma divided by the burn-off limit. We can prove this in simulations. These are the typical spectra that we collect from particles in the simulation at different value of the cooling strengths. And this is the cutoff of the spectrum as fitted with the exponential. And you see it going up as the burn-off limit becomes lower than sigma. So it fits with this sigma over burn-off limit relation. And we think that this is how you can get synchrotron in excess of the burn-off limit. So in order to explain GeV, you need this number to be close to 100. And we don't have the full model to explain what the actual value of the sigma is. And this is because we need to know the plasma density. And these current sheets are actually also producing their own plasma. This broad spectrum of synchrotron photons, they also colliding with each other and producing electron-positron pairs. We don't know how to scale our models to realistic parameters yet, so we don't know what the actual sigma is. But recently, just in November of 2023, there has been a exciting observation by Hess high-energy Cherenkov detector observing a Vela pulsar at energies as large as 20 TeV. So what they see in Vela is this GeV peak from Fermi, and then they see a separate peak standing out at the level of tens of TeV. So this TeV photons are telling us that there have to be electrons or positrons with energies as large as a few times this one in order to be able to produce these photons. So just from the fact that there are these photons, we know that the pulsar is accelerating particles to such energies. If you convert 10 TeV into Lorentz factor, you get few times 10 to the 7. And if we believe our theory that this is the value to which the current sheets are accelerating the particles, we'll see that this is basically the value of sigma. So if sigma is few times 10 to the 7, we plug this back into this relation to the photon energy, we get GeV for the synchrotron. And we can say that there are particles of these energies that would be able to produce this highest energy photons. We think that this 20 TeV is the inverse Compton emission that takes seeds of the low energy photons self-created by secondary pairs close to this current sheet, and then this low energy photons get upscattered by this highest energy particles, and that's how you get TeV. The catch here is that you don't see the same thing in crab. In crab, you do see something extending to high energies, but not a separate component. And my working hypothesis is that basically that the current sheet in crab, which is much more energetic, spins faster than Vela. It has higher magnetic fields at the light cylinder, and basically the pair creation inside the current sheet is so abundant that the sigma gets below this value. So the crab is not a good target to look for this standalone TeV signature, but pulsars like Vela and even older are good targets for the Cherenkov telescope array, because I think they would see multiple of this other TeV sources similar to Vela. I also have a clue of why the sigma is as low, but I think I'll skip that. You can ask me separately, but yeah, we have a model for this. So in the last 15 minutes, I'll talk about what I think is the most interesting subject, is how pulsars emit radio waves. They have actually been discovered as radio sources. The radio emission of pulsars is not the usual emission because its brightness temperatures is ridiculously high. In case of single shots from crab, it reaches all the way to 10 to the 40 Kelvin if you assume this as a thermally emitting source. So this emission is what we call coherent emission. It's not created by individual particles emitting photons and then summing up the intensities of all those particles. We think that this emission is produced by collective oscillations of the plasma. And if you create collective oscillations of the plasma, you sum up the electric fields. You don't sum the intensities. And that's how we think the collective radio emission of pulsars is produced. The goal is to understand how you create the conditions that the plasma basically decides to move together for a certain while and creating collective electromagnetic waves. Same thing we think happens in fast radio bursts, the extragalactic sources of extremely bright radio waves, and also in solar radio bursts. So pulsars are not the only astrophysical source that emits such radiation. And phenomenology of this radiation is very broad. You don't only record the intensity, but you also record polarization of radio waves. You typically find that the emission is highly linearly polarized, and you can measure what's called the position angle of the linear polarization as a function of the pulsar phase. And very typically, you see this swings of the position angle by as much as 180 degrees. So you see that the magnetic field in the emission region undergoes a huge sweep. And how do we know this is because the electromagnetic modes in the plasma, the radio waves, their polarization knows a lot about the orientation of the background field. If you solve your dispersion relations, you find that the orientation of the electric field is either along the magnetic field in the plane perpendicular to the line of sight or being 90 degrees across it. So the polarization of modes or any electromagnetic waves that are emitted, they know about the orientation of the magnetic field. And this polarization swing is very consistent from what you expect from the dipolar field. This is what's called the rotating vector model. You just calculate the orientation of the dipolar field in a plane perpendicular to the line of sight. As the pulsar moves, rotates, you would see different phases of that magnetic field. And there is an easy analytical prediction for how this curve should look like. And that's seen in roughly half of the population of pulsars. So you expect that the emission is produced somewhere close to the emission region, to the surface, where the magnetic field is quasi-dipolar. And the second argument for why this needs to happen somewhere close is that the width of the radial light curve across the whole population is consistent with the opening angle of this dipolar magnetosphere, basically to the size of this region where the field lines that open up to infinity actually originate. So somewhere where this pair creation and the current is launched, this is the region where the radio emission is coming from.
What sets the fact that sometimes there's two peaks, sometimes one peak?
Wait until the next slide. Yeah, so that's much more complicated than the gamma rays. So this is again a local simulation. Here I encourage you to tilt your head a little bit, unfortunately. So the neutron star is here on the left. The magnetic field is horizontal here. It's sheared out of the simulation plane. So basically it's rotating in and out of plane. And basically this represents the dynamics that happens close to the polar cap, right at the polar region. You see magnetic, basically this separate clouds of plasma that you produce that you saw in a global simulation. Now you see them much closer at a much bigger separation of scales. What happens here is that, okay, you create electric field, you accelerate the particles, they create photons, the photons get absorbed, they create pairs. These pairs then screen the electric field. So the positrons go separately to electrons, they create electric field in the opposite direction. Electric field gets screened, and the new particle that is extracted from the atmosphere cannot do anything. It cannot reach high energies because there is no electric field. So for a certain while, you don't see anything. That's because the electric field got shorted out. And you see this in this panel. This is the electric field along the magnetic field. You see episodes of when there is a deep blue color. This is where the electric field is strong, and then it gets shifted to smaller values. This is when the screening happens. So the process is intermittent. It keeps creating electron-positron pairs, but not all the time. For a certain time, the machine is getting a stop.
Is this the entire simulation? Where are these things created? Outside? You're saying them at boundary.
So the boundary condition is further away. I'm just zooming it close to the star. And this is where the acceleration and the photon emission is producing. So what you'll see further away is basically this clouds boringly propagating towards the right. And at the right, there is an absorbing boundary condition that says, okay,
So this is the
Particles now-
surface of the star.
yeah, so this is the upper 100 meters on top of the emission star. The sizes of the small regions basically are comparable to hundreds of meters. You have this little football stadium activity going on for characteristic neutron star.
Dark blue versus dark red is a relative change in density of water.
Yeah, so red means high density, blue means low.
But, and this, so peak here is 1%, 100%.
So the peak is 100, and this is with respect to what's known as the Goldreich-Julian charge density. This is the density that is minimal to exist in this magnetospheres in order to screen the electric field. So as long as you create something in excess of that value that is called the Goldreich-Julian, your plasma significantly affects the electric field. The value quickly reaches something like 100, and at that point, this exponential multiplication that I had described in the beginning stops. That's when the electric field gets sufficiently screened that the new pairs, they cannot be reversed by the electric field. So what you have further away is that there is this beam of the very high energy particles that was accelerated near the surface. It just moves as the very sort of heavy object. You cannot slow it down anymore. It just moves, keeps creating photons, and they get converted into electron-positron pairs. So the pair density rises as this cloud propagates away. And we think it reaches something like 10 to the 4, if you know how to extrapolate our models correctly, as this cloud goes away from a region comparable to the neutron star radius.
So in the canonical black hole magnetosphere picture, people model the multiplicity is above 1, right? So what's the difference? Because here you're only reaching Goldreich-Julian, you're not getting factors above it, or am I misinterpreting what you're saying?
It's quite similar to the black hole magnetosphere. The difference is that in black hole magnetosphere, the source of pair creation is different. You don't have strong magnetic fields, you rely on collisions of high energy photons created in this cascading region with the soft photons from the accretion disk. And the dynamics is actually, we think, is quite similar. You quickly get to values comparable to 10 or a few tenths in the case of the black hole. And later there can be something which is called the post-gap multiplicity, where this beam is propagating away and producing slightly more pairs. In that case, we think the multiplicity doesn't go to 10 to the 5, slightly lower. But this is because depends on the dynamics of different pair creation processes. So there is no conceptual difference, but there are quantitative differences because the mechanisms are different.
Yeah.
Okay, so the most important and interesting fact is that as the plasma is screening the electric field as it goes from blue color to less bright colors, so as it goes to 0, you see that this electric field starts to wane. And this is the waves that the plasma is emitting as the electric field gets screened. You would imagine that in simplest cases would be electrostatic waves. The particles would just move along the magnetic field line, redistributing by producing the currents that would kill down the electric field that was accelerating them in the beginning. What makes it electromagnetic is that the dynamics of field lines close to each other are slightly different. So you can plot the electromagnetic field. This is the magnetic field outside of the simulation plane, where we subtracted the magnetic field created by the current. So similarly to the neutron, to the actual neutron star, there's a current here, and it creates the averaged magnetic field. So if you subtract it, you'll see the waves created on top of this steady current. So you see that every time there is a screening event, as the electric field gets to oscillate, you also create waves in the outer plane component of the magnetic field. So basically, the message is that as the plasma gets to screen the electric field that was accelerating it, it produces electromagnetic waves. You can measure their phase velocities, they're superluminal, and you can then map them into the dispersion characteristic of the plasma, identify the mode that is obeying these properties, polarization and the phase speed. And from this fact, we know that this wave can escape from the magnetosphere. It would not suffer, for example, from Landau damping. such as the alpha wave would do. The alpha wave would just resonate with the particles and would not be able to escape. So this oblique screening waves are good candidates to explain canonical pulsar radio emission. In the simulations, we can also understand what the power is. It's at the level of 10 to the 4 times the spin down. This is quite consistent with what we see in young pulsars. And Libby Tolman, when she was a fellow at the Institute, she worked with me and she was able to construct a theory of how the screening process happens as it goes from huge coherent electric fields created by the neutron star all the way to this small length scales created by the fact that the electric field gets transmitted to smaller and smaller scales and it gets screened by the currents in the plasma. So we think we can explain the highest frequencies that are seen in radio emission of pulsars. We also speculated they could be seen in ALMA bands all the way to 100 gigahertz. Pulsars have not been seen yet at frequencies as high as that, but we think there is something interesting to look at there. So I think I'm 3 minutes away. I'll just mention the answer to Matthias's question about the different peaks in the emission beam in radio. This is 2 simulations that were created after the one in 2020. This one is done with Osiris. This one is done by Ashley Bransgrove here at PCTS. This is a local simulation where they considered the dipolar magnetic field with real curvature, and Ashley created a global simulation that was able to recreate similar dynamics. Basically, the message is that the discharge organizes it such that it operates very close to the polar cap and at the periphery of the open magnetic field lines. And as it does so, it experiences a huge inhomogeneity. The field line curvature goes up very quickly close to the axis, and it goes differently close to this last open field line. This is where the electric field has to match with this closed field line region where there's no current and no potentials or anything. So basically the answer is that these oscillations exist on all field lines going from the axis to the last open field line, but the pair creation is most inhomogeneous close to here and close to the center. And when these people record the Poynting flux of the waves that they see in their simulation, you can just measure the Z component of the Poynting flux leaving the neutron star. You can see concentration towards the center and to the periphery of the polar cap. And this is what's known in the phenomenological literature as the core cone geometry of the pulsar emission beam. You sometimes see just the polar region, or you see both the polar region and the periphery. This is what's known as the cone emission. So we think this is fundamentally linked to the inhomogeneity of the pair creation process next to the neutron star. So I think I'm out of time. I thought I will cover one more story, but that's good. So I'll just jump to conclusions. The pulsars are very interesting sources. They're creating electromagnetic waves across the whole electromagnetic spectrum. We start to understand them with plasma simulations. There are 2 interesting regions in these magnetospheres. One of them is close to the polar region where there is creation of electrons and positrons operating dynamically. This might power the radio emission that pulsars have been discovered with. And we think the highest energy photons are created in the current sheet beyond the light cylinder where magnetic reconnection is occurring. Thank you for your attention, and happy to take a few more questions.
Thank you.
Questions, please? Okay.
Yeah, the story of the polarization angles, this assumes that whatever mode you're creating is evolving adiabatically as it propagates, right? Like an O mode will
Yep.
retain its relative polarization relative to the magnetic field. Is this necessarily true if it encounters upstream inhomogeneities coming from, say, previous discharges?
That's an excellent question. There is, what Anya is saying is that if electromagnetic waves propagate through the plasma, if the scale of the inhomogeneity is very large with respect to the wavelengths, you have what's known as the geometric optics being applicable, and the polarization of the wave should track the evolving characteristics of the background magnetic field. So as the magnetic field rotates across the wave propagation lengths, its position angle should change. What's being calculated by Mel Ruderman in the 70s is that you can calculate what's known as the limiting polarization radius. So the radius at which there would be a transition between this adiabatic walking behavior, the wave tracking the geometrical optics assumption, to the place where the plasma density drops and basically propagates like in vacuum. So if you assume uniform filling of the open field line cone by the plasma with multiplicity of 10 to the 4, you'll get that this polarization limiting radius is comparable to a fraction of the white cylinder. So actually quite far in the magnetosphere. And that actually is seen in some pulsars. You see, instead of this S-line curve, you see a flat position angle. That's a feature of the toroidal field in the wind. It doesn't matter how you go through the toroidal field, its direction is the same in the plane perpendicular to the propagation of the ray. So in that case, you would see a constant angle. And that is seen in millisecond pulsars, but not in these young pulsars. So what I think is the key here is that indeed there is homogeneity in the plasma distribution, and basically the polarization is fixed as long as the wave escapes from its own cloud. As long as it escapes from its own cloud, it feels basically a vacuum. And I think that can shift the polarization limiting radius to be closest to the star. So yeah, the short answer is I think both things are operating, and in different pulsars you can get different zoology.
Yes, so you mentioned these two mechanisms. I wonder, do you expect to see both of them, the same pulsar? It seems one is from the polar, the other is from the equator.
Right. So since the current, if it would be an aligned rotator with magnetic axis along the rotational axis, they would beam exactly orthogonal to each other. But when the pulsar is tilted, the current sheet, the beam created by the current sheet, is actually much broader. So you could see the different lines of sight. And that's what we think is happening in Vela. In Vela, you see radio emission from the polar cap and the gamma rays from the current sheet. In Crab, we think we see gamma rays from the current sheet, radio emission from the polar cap, and also radio emission from the current sheet, which I was not able to cover.
I was about to ask exactly this question. How do you manage to make the radio emission and the high energy emission coincide in the phase in the crowd?
Right. So the idea there is basically that these current sheets are they can also produce radio waves. So this is the reconnection simulation in a periodic box. So here there is no neutron star anywhere in the box. You don't have to remember about it. What's done here is that you just have two opposite field line polarities meeting in the center, creating this current sheet. And I'm sure some of you saw many of the simulations with various people. What's plotted here is the Poynting flux. So the Poynting flux in the simulation, the E cross B in the direction towards the current sheet, minus the Poynting flux that reconnection creates by advecting the plasma inside the current sheet. On top of this net Poynting flux, you also see all sort of waves, almost like you have waves on the surface of the lake. You see the spherical waves propagating away from the current sheet. What we think is happening is that these plasmoids, the relativistically moving bullets that have strong magnetic fields, they collide with each other, and when they're colliding with each other, they're creating time-dependent electric fields and magnetic fields, and that basically serves as little antennas operating across the whole current sheet. And each individual collision is producing bright electromagnetic waves. And this emission would be in phase with gamma rays. And we think in Crab, this would be also at radio frequencies. There is a theory in this paper explaining why you would only get the frequency if the magnetic field is around 1,000,000 Gauss. If you move lower than that, this radiation basically will just become very low frequency. And someone asked, I think, about the variability. The radio is variable on time scales all the way down to the nanoseconds. You see individual bursts that have the frequency times duration of order a few. And then you also see enhancement in X-rays. NICER 2 years ago saw an increase in X-rays coming together with the shots of radio waves. So all of this millisecond and lower timing observations in X-ray and radio are telling us a lot about the dynamics of reconnection inside this condition. Surprisingly, you can learn things happening on 10 centimeter scales all the way down in the center of the Crab Nebula. I guess at that point I'll stop.
Thank you.
Thanks so much.
Thanks.